So I have a control region here, a box marked in yellow, and I'm going to consider a flux going through the box. So let's make this the x-axis. So let's say this is x here, and x plus dx in this direction. And then let's call this the y direction. So we'll say that this little distance in this direction is dy, and this little distance in this direction is dz. And so if I consider some sort of flux going through in this direction like this, then let's call that n. So this is n dot. So this is the flux in this direction of species I in the x direction. And this is going to be in terms of mass. So this is kilograms per meters squared per second. And if I want to know how much through this little volume here, how much of species I is passing through, then I just need to multiply by the volume, by the surface area rather. So this is multiplied then by dy dz. And so the total, so if I just consider the total units here, then this is then kilograms per second of species I passing through this wall on the left. And I can do the same for leaving this little box, this little region in the x direction. So let's measure the flux coming out of this box. And I'm going to denote this as n dot, so species I at x plus dx. So this little just moved along the length of this box here. And again, if I want to know the total amounts going through this box, I have to multiply by the surface area. So then this is going to be multiplied by dy by dz. So I can measure the flux going in and out of each wall, but I can also, if I know how the flux is changing inside the box, then I don't actually need to measure the flux coming out here. I can rewrite this as simply the flux coming into the system of species I, so flux of species I at position x, plus then the gradient. And actually this is a partial differential, so the gradient of species I in the x direction with respect to the x-axis multiplied by the length of the box, so in this case dx, and then multiplied of course by dy and dz, which is the surface area. Now, just ignoring for the moment the flux in the y and z directions, if we look at the flux into and out of the system in the x direction, if the flux into the system is greater than the flux out of the system, then the density inside the box is going to increase. And obviously, if the flux out is greater than the flux in, then the density in the box is going to decrease. And this can be expressed fairly simply. We can simply take the difference between the two. So the flux into the box multiplied by the area, and subtract away from that the flux out of the box. So it's x plus dx, again multiplied by the area. This is equal to, well, if these are the same, then this is obviously 0, and if they're not the same, then this is non-zero. So we can express this in terms of the change of density per unit time multiplied by the volume of this area. So this is actually then the change in mass per unit time inside the box. So these units are all the same. And then if I substitute this term on the right in here, so this is the flux into the box of species I in the x direction, dy dz, subtracted away from that, this flux into the box species x of species I, plus and then the gradient, so the gradient of species I in the x direction multiplied by the length of the box in the x direction multiplied by dy dz, and then above here this is then obviously the change in the mass or the density inside the volume here. Now I think you can see immediately that some things cancel, so this cancels with this term because this is just subtracting the same thing, and then if I need some more space, so if I just scroll down a little, then we can rewrite this. So this should be negative, of course. This is the negative gradient of species I in the x direction multiplied by dx dy dz, and this is equal to the change in the density. And then again, obviously these dx, dy, dz, so this is insensitive to this volume term. And so if I just flip this round, what we're then left with, let's just write this over here, so this is the change in the density per unit time is equal to the negative change to the negative gradient inside the box in our little model here. And now I've been ignoring the y and the z directions, but obviously if we just only considered one direction, then this wouldn't necessarily be true, because if you have, and say if the flux into the box in the x direction is greater than out of the box in the x direction, but maybe you have the opposite in the y direction, then maybe they cancel exactly and you end up with no change. And so what we need to do is to consider all three directions. And you can derive this for all three directions, but it's a little bit long. So we can add to this. So I'm just going to tell you what. Let's just copy this over. So in addition, so this is in one direction. So this is just to highlight. This is x direction, but it's not really rigorous. What we need to do is to include all three directions, and so this is it's a simple linear combination. So this is the change, the gradient of species I in the y direction, and then added to this the contribution, obviously it's negative, of the gradient of species I in the z direction. And I shall just underline this because this is kind of what I was aiming for in this video. So this tells us that if we know the gradient of the flux in all three of our Cartesian directions, then we can calculate how the density in the system is changing with time.